Okay, so this video is going to be kind of a rambly explanation of how the rover software works, how the ground station software works, a little bit about what I was thinking when I designed them the way I did, as well as just some things to keep in mind, some useful tools, just kind of a rambly covering of everything I can think of to make working on the software a little bit easier in the future. So here I have the rover Git repository opened. It's the root, so it has electrical and all the other teams as well. But I figured I'd start here because this has two files, ground station git reset and rover git reset, that are both important. Because essentially, whenever I was working, and I use PyCharm for my work, so I'd set it up to have automatic deployment working. I'd make changes, I'd hit save, and it would automatically upload the changes to the rover or the ground station or whatever I was working on. Once I got it to a point where I knew that things worked the way I wanted, I'd commit it, I'd push it to the GitHub server, and then I would run these git reset scripts on each of the systems to pull them back to the git committed version of the repository. And then for the rover, for example, I'd restart it, get it to reboot with fresh scripts, and then make sure that everything still worked so that I knew that what got committed to the GitHub repository was in fact working. So I just made some scripts to do that. In the case of the rover, it's pretty easy. The ground station, I did a little bit more because I didn't want to cache all of the maps that were being downloaded. So I was telling it to copy all the map files out and then nuke the folder, pull a clean version, and pull them back. Maybe there's a smarter way to do that. Maybe simple sim linking would have been smarter, but I was very sleep deprived. Didn't matter. It works. So that's what it is. Feel free to modify it if you want. The important thing here, though, is the software folders, and so that's what we're talking about. Again, there are two scripts in here, ground station setup and rover setup. These are scripts that I used when I wanted to add or change a ROS package that I was working on, really only for adding or removing, actually. So I'd tell it all the ROS packages that I want, and then running these scripts would symbolically link the correct packages into the catkin workspace folder on the rover or ground station respectively. In the case of the ground station, it also make sure that a key file needed for talking to Google Apps Script was there. Again, just things to make my life simpler when I'm constantly playing with setups. Doing this by hand was really tedious, so some scripts made things a lot easier. Okay, so I think I'll start from the rover side because you can't do anything with the ground station if the rover isn't there. This is also going to assume that whoever's listening to this has a decent amount of familiarity with ROS, because if you don't, you're going to have a bad time anyway. So anyway, ROS runs with a ROS launch file. In the case of this software, I have a rover main package, essentially, ROS node, that has launch files in it for the ground station and for the rover. So to run the full software suite on either the ground station or the rover, all you have to do is run ROS launch rover main and then either ground station.launch or rover.launch respectively. And I kept all these ROS packages together under this single ROS packages folder, including the ground station, because there were so many custom ROS packages that I didn't really want to be dealing with, having to manually copy out generated Python header files and all kinds of other stuff that the catkin make process would do for me, when I could just symbolically link all the packages in both systems, let catkin make deal with it, and then have it at a system level and have it be fine and easy. Again, I don't know if that's necessarily the 100% correct way or the best way to do it, but it seemed to work pretty well. Definitely didn't hurt anything, and it definitely made things easy because it meant that most of the stuff I was editing was right here in this one folder, which there's plenty of stuff in here, but it definitely kept things a little bit more compact. So anyway, on the rover, on both rover and ground station, actually, there is the user's root folder. On the rover, it's /home/nvidia. And then I made a folder called GitHub with capital G, which is where I cloned the rover directory, this entire Git directory here. And then inside of it, it would have the whole stack, and then I just use different parts of it depending. So in the case of the Rover, one of the first things that it got that was different is it used some of the stuff here in this environment folder. Again, naming conventions, I don't know if it's necessarily the best name, but the environment folder is everything that's kind of having to deal with the environment itself and not the actual software that's making the Rover run. In this case, I really only have a Rover folder, but there's important things in here like the auto power off script. This is automatically started at boot, and essentially all it does is check to see if all of the iris nodes have disappeared, and if they have, then it's assuming that there's been a power off, the switch has been turned, and it should shut down. So that's a pretty straightforward script. It actually uses the UDEV rules to, which I haven't even talked about, UDEV rules to determine what it should be looking for. So let's talk about that a little bit. There's a UDEV's rules folder here, and there's one for the cameras and one for USB serial devices. If you don't know what UDEV rules are, they're essentially files that tell the system, tell Linux systems specifically, how to map devices that are being loaded at a low level during boot time, or in this case, when they're plugged in over USB, to a particular part of the system. They do a lot more than that. It's a bad description of it, but for example, if I just show you it, essentially what it's doing is it's saying, look for a device that's plugged in that is part of the teletype system, which in this case is the serial device. Serial device is plugged into the Rover. Look for ones with a vendor ID, which all of these three items are things that are passed in as serial information. You can find them by typing USB-devices at the command line. So it says find one with a vendor ID, blah, product ID, blah, serial number, blah. And then in the case of these, because they're USB to quad serial adapters, they have 4 ports on them. So it says map a particular port on this device to this name. So what this means is that when you plug in a serial device on Linux, you get /dev/tty USB 0 or USB 1, or in some cases ACM 0 or ACM 1. What this let us do was tell the UDEV system to add a symbolic link, hence the symlink, at /dev/rover, and then give it a name that we care about. And this was pretty much a requirement. If we couldn't do this, making the Rover systems work would be a lot harder, because every time you turn the system on, there's no guarantee that devices are going to come up in the same order every time. And so what this allows us to do is say, I don't care what the order is, I just care what the serial number is, and I care what physical port on that device I care about, and now that it has a name, and every time I reboot, that name is going to be the same. It doesn't matter if the actual device path is different, it's always going to come up with a useful name that you care about. So in this case, the Iris board has 3 quad serial adapters on it, so here's all 12, and they're all mapped to names that we care about, except for a couple that aren't even plugged in. So this is super important. Without this, you'd have to do something horrible like open every serial device and have the first thing it does be it send out like an ID or a string telling you what it is, then you have to dynamically map it to the thing that it should be. It's just a giant pain. So this solves that problem. As you can see down here, there's like a special one for the ARM because it's on its own USB to serial adapter. And then the same thing happens for cameras, where we can say, hey, camera with a serial number this, map it to a name. So we can say, okay, this is for sure the Z camera, this is for sure undercarriage. And now it doesn't matter which USB port you plug it into, it's just this serial number device shows up, and now we know it is camera undercarriage, and it's always camera undercarriage, and it makes things really easy. So again, there's a script here. It just copies them to the right place on the system and reboots so that it can install the rules. So anyway, that's needed. Then you get the names for things, and that matters. So in here you have all of those devices. So it actually uses that UDEV file to determine what devices it should be looking for. And again, if it hasn't seen any devices for a certain amount of time, it shuts the system off. This is part of the smart power off feature because the Jetson TX2 is on a UPS. So essentially it says, hey, wait 5 seconds, If I haven't seen any devices in 5 seconds, assume that we've shut the rover off and it needs to power down. So that's all this does. One thing I can say for sure is that this needs an extra check that says if the script has just started, like if this is the first time that the script has ever ran and it doesn't see any devices, don't power off. Just exit the script. Because what happens is that if you're doing a serious debug, or let's just say that Iris dies, which is the worst case scenario. If Iris dies and the USB devices never show up on the system, this script starts and it'll immediately shut back down. You won't even get to launch the rover scripts before this thing powers the system off. So really need to change that while Iris is working fine, which it has so far. And while everything is fine, it's no big deal. But we did encounter a problem where on the first generation of Iris, when it died, I couldn't even boot it up to the system to see what was wrong. It just kept powering down, and I eventually figured out it was this. We plugged in a new Iris, everything was fine. So just something to keep in mind. So anyway, that's the auto power off. On the flip side here, there's also startup stuff. So one of the things that I learned at one of the jobs that I worked at was this neat trick where the tool screen, which is a really old tool, I think it's been around a really long time, it will let you do some really neat tricks that make working on a remote system much easier, especially when you're dealing with scripts that you want to be able to actively monitor and not just be digging through log files, maybe actively interface with it, change things. So what it is, the screen is a tool that lets you have multiple terminals in a single terminal. So like you could SSH to a system, run screen, and then use like command line commands to tab to different sub screens within the single screen. And this is, today that's fine. You have GUIs, you can have multiple windows, you can have tabbed groups on a real window. It's easy to do, but this was designed back when all you had was a terminal. So anyway, that's what screen is, and what we can actually do then is tell screen, which, here we go, tell screen that when it launches, it should make a tab in the terminal called Rover main. What it should run is this startup script. And then we're going to open up another tab that's just a shell, and you're done. And there's a bunch of other configs to change how things look. I grabbed most of the config stuff off of a GitHub repo and then just changed this part. And then in the startup script, it's as simple as sourcing necessary files to make ROS work properly. Here's where the auto power off script is run, and then run detach so it can just keep running in the background. And then it just runs Rover main and you're done. It then also executes bash at the end so that if you hit Control-C on the script, you go back to something and it doesn't just kill the tab. So this config says when, if you pass this config to screen, it'll create this entire environment, it'll launch the rover, and you'll be good to go. So what isn't in here is that I set up a system service on the rover that actually launches this at boot. So it launches it. The actual service name is called screen at NVIDIA. And again, it was another thing that I found online that was, hey, here's how you can set up a service that starts at boot and runs in the context of a particular user. So I made it screen at NVIDIA, and it makes sense. So if you actually go to the rover and you say sudo service screen at NVIDIA start, stop, or restart, you'll be able to actively control this entire process. Now, what's cooler about the whole setup is that while you can use the service commands to actually control how the startup scripts or how this entire environment is running, you can also attach to an existing screen session while it's running, even if it's in the background. So if you SSH into the rover and you want to see what the scripts are doing, all you have to do is type screen space -r, and it's -resume essentially, and you'll be dropped right into the screen session. You'll be able to actively see the scripts as they're running. You see errors, it'll have the whole history since boot, and it's super simple. And then if you want to disconnect from it and leave the scripts running. You went in, nothing was wrong, and you want to go out, you do Control-A-D for disconnect, and then, or detach, and you get dropped back to a normal bash shell on the rover, and all's good. You can go in and out as you want, and everything's great. So this is super, super useful, rather than having to, SSH in and like kill a background process and then start a new foreground process and then debug it, and maybe it's some weird glitchy issue that you're having, so you really want to be looking at the existing logs of things. This just turned out to be a really nice way to do it. Shout out to Jasmine at the Ocean Mixing Group Lab for being the person I saw this from. It's a really good way to do it and makes things a lot nicer. So anyway, I think that kind of explains, that's the rover environment. So you have the repo, you have startup scripts, a service that starts the rover at boot time. It also means if you don't want it to start at boot, you can just tell the service to stop, and the next time you reboot, it won't happen. Again, very useful things. But with that, with the service running, you turn the rover on, it boots up, and it takes the 40-45 seconds, and then the scripts launch, and the rover is running. So at that point, it runs again, rover main, launch, ground station, or rover.launch. And then most of these files are just including other launch files. This is just a very ROS way of doing it. So there's a bunch for rover and a couple for ground station. And there are a couple in here for testing and such, but overall, I try to keep them pretty compartmentalized, even if it was very simple, just to keep my sanity. So yeah, so each of these files themselves should be pretty self-explanatory if you understand ROS at all. And I've also named them pretty self-explanatory, I think. So for example, in the rover, I'm starting the control system, the arm, science system, cameras, statuses, and then the topic transport senders and receivers. And then in this case also the odometry node, which was my second revision of it, and that's a whole nother issue I'll talk about a little bit later. Let's see, so under control, let's start there. We have the iris controller, bogey controllers, drive coordinator, and then all the miscellaneous systems like the tower pan tilt, chassis pan tilt, all of the effectors. So that includes like the gripper, the mining system. And then here, for example, was the scale system, which was an emergency thing kind of tacked together that just ran on an Arduino hot glued inside the rover hours before competition. So that's been commented out. I will explain this group here real quick. So the iris controller is the node that actually talks to iris itself, because iris is two things really, right? It's a 12-port USB serial converter, and there's also a microcontroller on one of those ports. So this talks to that microcontroller and pulls in the SBus data from the FrSky controller and says, okay, here's control data to actually use to drive the rover manually when you don't want to do it from the ground station. Honestly, from being a competition, that is one of the most useful features we've ever decided to add to the rovers. It's a simple, ease of use thing that really makes a difference in how painful dealing with driving the rover around could be otherwise. So anyway, iris controller brings in control data from the FrSky controller. And then each of these nodes kind of makes sense, are the raw nodes that talk to the motor drivers on the bogies. And then you have the drive coordinator. And the coordinator is the important thing. Honestly, the name should change from drive coordinator to probably control coordinator at some point. Because what it's doing is arbitrating between the drive controls coming from the ground station and the drive controls coming from the FrSky controller. So actually, maybe the drive coordinator is fine, and there should just be extra coordinators for things like the arm control, for example. I don't know, there's plenty of ways to do it, but essentially all it's doing is saying, hey, is the FrSky controller on, and is the dead man switch in the mode that says, hey, the FrSky controller should have priority. If so, accept the commands from the FrSky controller and ignore the ground station. Otherwise, if the deadman switches in the other position where it cares about ground station, or if the FrSky controller is just plain off, assume that the ground station is all that's left, accept it, and then you're good to go. So it's a pretty straightforward little coordinator there, but this is something that could be worked on in the future. You can add in control for things like the arm. Honestly, that's one of the nice things about having all of this be in ROS at this point, is you can make the controller do whatever you want to. If you want to make the arm move from the sticks, you could just have another switch on the FrSky controller, flip it over, and then suddenly the controls on the Rover or on the FrSky controller move the arm instead. It's really whatever you want. You can make it do the pan tilt systems, you can make it do the mining systems, literally anything. I consider that to be a very secondary extra frilly feature, so I only did it for drive and never got a chance to add anything else. But that's definitely something that could be added in the future. Okay, so that's control. Arm was pretty straightforward. It's just launching the arm node. Science, again, very simple node. It's just handling the either the radio direction finding system or the soil probe, depending. That's also something to note, actually, is that for the science and the effectors node, both of those are timeout based changeovers. So for example, on the science one, since that's a little bit simpler, you have the radio direction finding or the soil probe systems. So what it does is it opens one first and it says, okay, let's assume RDF is here. Let's talk to it for a bit. Oh, I couldn't talk to it, and it's been, this many tries or this timeout. Okay, swap over. Let's see if maybe the soil probe is there. Yes, it's there. Okay, broadcast data or accept commands or whatever it is. And then if not, assume that there's nothing there. It kills the node, and then if you notice, there's a respawn command on all of these, which means that if I mess up code, or if in the case of these systems, if just by the way they work, they're waiting for some piece of hardware to show up before they can actively do anything, it'll just keep dying every once in a while and restarting and waiting for the hardware to show up, and the respawn makes sure that that happens. There really is no reason to have this set to off or false, because this can really save you when something is wrong, or in the case of Iris actually having problems, which it did this year, where on a semi-regular basis the entire USB hub on Iris would just drop out and we lose everything. And then because of the way that I wrote these nodes, respawn would just kill all the nodes, restart them all, and we'd have control back up in a couple seconds at worst. So again, leave those there. You really want those and make things nicer. Let's see, what else was in Rover? Cameras, again, I wrote a custom camera node. There are a lot of things that I would probably change about this node. I don't know if I really want to get into it because it does work the way that I want it to. Again, basically all it does is it opens up each camera at a fixed resolution, and then based on commands from the ground station, changes which resolution it's currently broadcasting. And then that just basically is adjusting how much bandwidth is being used, and then the ground station does some auto quality adjustment, and that's all good. Ooh, this is an important little note here. This little appendation of this command here basically says run this node on core 1 or 2 or 3 or 4. Task set is just a Linux command that is what it says it does. It sets the task on a particular core. So if you wanted to run the ls command, you could do task set -c1 space ls, and it would run ls on core 1 just because he told it to. It's a really neat feature on Linux. It's really easy to set a particular process to run on one core or on particular cores. And this made it really easy to partition out CPU usage a little bit nicer, because these camera nodes especially are pretty high performance. They use most of the core that they're on. So it was nice to be able to make sure that they didn't accidentally start on the same core and then have to deal with the overhead of moving them to a different core. It started where it needed to and it stayed there. This, I feel like, will get extra important if the software team in the future figures out how to deal with getting the Z involved. I did have the Z running at one point, and the nice thing is by doing this and then running the Z on top of it, I was able to get very high utilization on the TX2, but not unreasonable. Like, I still had enough overhead to run extra stuff. So anyway, I ended up doing that, and it seemed to work pretty well. Status system, I'm just going to mention that all it's doing is looking at ROS topics and then waiting for them to change, or on a periodic cycle broadcasting specific statuses. Some things I just didn't care about coming back to the ground station all that frequently, and this was a very easy way to do that. It also handled some other things like processing GPS data to get like the number of satellites available, other miscellaneous things that the raw nodes that process them didn't provide, but we still wanted. So these status nodes, or this status node does that. I'm going to skip these transports for a second, go to odometry. Right now, odometry is one of the biggest things that fell through on this year on Rover. Number one, you have to start the Rover with it pointing true north in order for what's showing on the ground station to be correct. That really shouldn't be the case. With the IMU we have, it should be possible to not have it be that way, but I couldn't get it calibrated such that it would. I'm not sure what the issue is there, but I have found a way to make it work, right? You turn it on with the pointing north and it worked, and I didn't have time to deal with anything else, so I called it good. But essentially, this package running right here should have been enough to get the where is it? The robot localization package, giving a state estimate for where the rover was, combining the IMU data and the GPS data. I'm just going to keep it short. I couldn't get it fully working. I got it such that all of the data was where it was supposed to be. Like this node was doing something, but it wasn't doing what it was supposed to, and even worse, it wasn't doing what I had tested with in like January of 2018. I had it kind of working, and then we installed the real thing on the rover, and I never got it working properly ever again. So that's definitely something to play with. But anyway, otherwise, there's an odometry node that is what talks to the tower node, pulling in GPS and IMU data and separating that all out so that this package can even use that data. And then all of this is just, there's an AVSAT driver that parses the NMEA strings into a fixed message, and then the localization package which needs that, and this one extra little node down here. Oh, you can also see this is all commented out right now. This one other node that does like a single shot update to this system when it gets a message from the GPS. Honestly, I don't even entirely know what this is doing. This was a pretty complicated part of the rover that I never quite got figured out and had other things to work on, so it's one of the things that fell through. Good luck with that one. It'll take some work. I mean, I know it's possible. Like, tons of rovers use it, quadcopters running ROS use it. It's not like it's unattainable, it's just I didn't have the time to make it work. Okay. Now on to the Nimbro stuff. So one of the biggest issues that we had last year, not this year that we just won, but the one previously, was communications. This year I really wanted to make sure that the communications were the robust thing. Part of that was changing over to the new radios. The other one was making sure that we didn't push too much bandwidth that we had options for changing how much bandwidth was being used, basically having the flexibility. So things like the low res mode on the GUI, where it's like we're really, really far out. We just need a little bit more bandwidth because it's getting too choppy. You hit the button, everything drops to low res. You can even turn off 2 of the displays and you just get one low res view, and you have enough bandwidth to actually drive out, drive somewhere else, keep driving if before you weren't going to be able to get there, and then you're done. So one of the things that I found that really helped with the kind of control we are getting and the video latency that we're getting is this ROS package called Nimbro Network. And essentially, it is a package made by a group that uses it for the transport layer between their base station and the vehicle they have running the DARPA challenge, to transmit massive amounts of information, to transfer real-time control information, basically anything they want. So what they wrote is a topic transport. So normally in ROS you have that ROS master, and then all your nodes run, and the ROS master coordinates sending them all where they need to go. And if you want a second physical computer to talk to the nodes on another computer, you'd tell it where the ROS master is, and then it would connect to that. And rather than starting a ROS master locally, it would just use the remote ROS master, which is great if you have very consistent networking. But I found that when you were in weird networking environments, especially ones where you've got full dropouts, you could end up in states where it could never successfully reconnect, or the reconnect would take forever. It would just take an unreasonable amount of time. So I went looking and eventually found this. And so what you actually do instead is you run a master on the Rover and you run a master on the ground station, and then you run instances of this node using a sender and receiver. So the Rover sender would connect to the ground station's receiver, and the ground station sender would connect to the Rover's receiver. And it would not only send the topics over the link, but you then had the option of telling it whether you wanted UDP or TCP for sending the data. And if you're using UDP, you could also rate limit it, which was super convenient because that meant for things like the cameras, I could say, okay, send the data from this stream to the ground station, and I'm going to limit it to 30 frames a second, because that's the max I'm ever going to want. I can turn on compression too. It also has built-in compression, or compression flag at least. And then it being UDP, we could lose entire packets. And again, for like a live view of Rover video, if we miss a frame here or there, that's fine. That is ideal if it's the difference between missing a frame or building up a massive queue in TCP and doing error checking and having massive latency. So you want UDP for video. And then the worst case is you get really choppy video when you get out at range, but at least you have it. Same thing goes for control. When you're driving the Rover, everything that I'm doing is running through a watchdog. So if it doesn't get any control data in a certain amount of time, it should just stop. So essentially, if you're just spamming it control commands, and then you rate limit and you say, okay, I only want to let through 20 commands a second, and you have 2 commands that are very, very close to each other and one of them gets lost, you're probably not even going to notice it. If the timeout on the watchdog hasn't hit, it's just going to keep running. It's going to feel smooth. If it's getting, it just works. You want TCP for the live control, and you have to be smart about what you're doing. So it's like you're going to use TCP for live control, live video, and then things that matter, things that you need to get from one place to the other, even if it takes a while, you'd use TCP for. So for example, if we were enabling autonomy and we just had a whole list of waypoints, you'd hit enable and it would send over TCP the whole group of all the waypoints, and it might take a second, but it's either not going to get there at all or it's going to get there in full, and that's what you want for TCP. So anyway, this package did a great job. I was able to get live control, live statuses, and 3 concurrent video streams at 640 by 480 pretty consistently. We had it running up to a kilometer. To be fair though, at a kilometer it wasn't running at 640 by 480 anymore. It was at 256 by 144. But the thing was that it was really pretty stable for control and video over what was essentially just Wi-Fi, which is impressive. And this node was a major reason why that worked. So whether you're the OSERC Mars Rover team in the future looking at this, or another team watching this, I highly recommend looking into this because it's a really cool little tool. Okie dokie. I think that was it for Rover. I'm going to go into the ground station real quick because it's even simpler. It's just those senders and receivers, and then it launches the ground station. Simple as that. So again, on the Rover, I don't really know if there's really anything else left to talk about. I'm not going to go super in depth into how the Rover software package works because they're all pretty straightforward. It's like, you know, Rover Science, you have a Rover Science node, bunch of defines, you have a class, runs the class down here at the bottom when it launches, and connects to an instrument over a serial port and runs. Like, I could go through all these in depth, but ultimately I recommend that this is something you play with, especially when it comes to Modbus, because there's a lot of nuances to how Modbus works, and things like setting delays and timeouts are really important. If you set things wrong, it'll fail to connect even though everything you need is there. All the electrical connections are fine. So I would say just kind of study these files. They're not that long really, and I tried to be very smart about how I name things so that they aren't unreadable. But play with it and see how it does. See how it works. And you know, there's a lot of stuff here that's also very specific to ROS that you just need to know from having worked with ROS. So for example, like this is getting a parameter from a ROS launch file that's in the local context with name port, and then if it doesn't have anything passed in, it's pulling from a default port. This is all stuff that you just kind of have to play with Python's ROS libraries and be familiar with before you fully grasp what it's doing. And ultimately, at least for this next year, I should be semi-accessible to be asked questions about how all this works. So what is more important now then is I'm going to switch to the ground station. And I'm going to talk about that a little bit. First things first, excuse me, in the scripts folder, this is the thing that actually launches the ground station GUI. So again, it's just doing a little bit of bookkeeping and then moving a key and then running the ground station. It's really nothing special, but it needed some of this stuff in order to work properly. So again, made a script, made it easy. That's not the important part. The important part here is in source, where you have the main launch file. And I'm just going to go ahead and start here. So the ground station software is big. If you just look at the imports that are needed in the main file just to get the thing to launch and have all the parts running, there's a lot of subsystems in the GUI, which isn't surprising considering it's spanned across 2 monitors and it's doing that much control and that much status indication. I think I would say overall most of the systems are pretty small, minus the video one. So video and mapping really are the 2 big systems. Everything else is pretty compartmentalized and small. But it's a big program. You need a pretty good understanding of Qt, specifically PyQt. You need to have a good grasp of multi-threading and how Qt handles multi-threading and inter-thread communication using signals and slots. And then on top of that, you also need to know a little bit about how ROS's callbacks for talking, for receiving data from topics goes, and publishers in Python for publishing from them. You need kind of a good understanding of all of it to really get an idea of how this works. But we'll start here. So basically, every subsystem on the rover is part of the framework. That's what I called it. So under framework, you have ARM systems, control systems, logging, etc., etc. So under each, you'll have something like ARM indication. And then I could have done a blanket import, just import star, but I really wanted to be explicit so that I knew what I was doing and knew what I was adding. I didn't want anything getting pulled in that wasn't very explicit while I was working with something so large. Not the most elegant, but it worked pretty well, and it kept things consistent. So this entire file is basically nothing but creating the instantiations of the windows, the full screen windows that got shown, and adding all of the classes to it, starting all the threads, and handling quitting when you hit Control Q at the end. So there's a lot going on here for that. Really, the only things that a future software developer for this really needs to know is that you should only really be editing this section here. You'll add a new import, and then you'll either add a non-thread or you'll add a thread. You give it a human readable name. Make sure that there are no duplicates. If you make them duplicate, it will break. And so you give it the name, and then you give it the instance of the class, passing in this object self.sharedObjects, and that is instantiated right here. And essentially what that is the system-wide object that gives you access to the UIs for the screens, to every class, both threaded and not. And without it, you wouldn't really be able to make the signal slot systems in Qt work. You have to have access to this class to make things work. And this was a very simple way to give you access to it without breaking things. Something also to note is that when you're adding something with a thread, let me look at something that's simpler, hopefully. That's in with RDF cores and MISC systems. Your class needs to have a couple of things. First and foremost, it has to have a run method. That's what actually runs a QThread subclassed class. But you need these three functions down here. OnKill threads, setup signals, connect signals and slots. You're going to edit signals and slots all the time, but setup signals and OnKill threads should never be touched. What is here should stay the same. Don't touch it, don't mess with it. Keep this function name the same, and everything will be fine. This run thread flag you need to have, and then in run, it needs to say while the thread is running and do everything that you want to do work-wise inside of there. If you keep those things that way, if you were to gut one of these and leave just these three functions, put a pass in here, delete all this, put pass instead, put run and like put a print right here and nothing else, and add it using this, you should instantly see a thread be added, thread start, it should print out on the console, and everything will be taken care of for you. If you decide not to do it that way, you're on your own. I tried to make it a little bit easier because I had so many threaded classes that I needed to add, so I'd recommend using it. So beyond that, there are just a lot of classes here. Some of them don't do very much, so things like the mining system, let's take a look at that, mining core, are not even threads, they're just objects, and all they're doing is connecting to GUI elements. I'm saying, connect to the camera's shoot button on the left screen, and then connecting signals and slots saying, hey, when the button's clicked, run these methods over here, which in this case are just using the ROS publishing system to publish a particular command to make the mining control do something. Others are a little bit more complicated, like RDF core, which is not only subscribing to data from ROS, but then actively processing the data, doing windowed averaging, doing it fast Fourier transforms on it, and then broadcasting to the GUI an update. I will mention, I'm not sure who is listening to this, how much experience they've had with Python and Qt. If you ever run into an instance where you're trying to update a GUI element in PyQt from a thread, and it isn't crashing, but it doesn't seem to be working, or it's working inconsistently, it's probably because you're trying to update the GUI element from inside this run thread. When you're in this thread, you're no longer on the GUI's context. And if you're not on the GUI context, you will break things, and it won't always crash in a way that makes sense. If it crashes at all, so what you need to do is make a custom signal as part of your thread. Use signals and slots to connect the signal to the appropriate update method of the element. So in this case, I would say, hey, I have an RSSI LCD number update ready. I'm going to connect that signal to the RSSI LCD numbers display slot. And then when I want to show it, I'll say, not the RSSI one, but you get the picture, this signal dot emit the thing I want to show. If you don't do it that way, it just isn't inconsistent. There were times where I had it work for days, and then it just stopped working entirely, and I couldn't figure it out, and it just turned out to be I was updating it manually and not using the signal slot system, and it was just broken. So there's going to be a lot of bookkeeping work in this to add a lot of copies of things to make stuff like this show up. For example, an arm indication. Look at, there's all my custom signals for that. It's not compact, but it works, and it works consistently. So honestly, that's all I can ask for. Also a little note here. Like, for example, I want to get access to the right screen. Now all I have to do is just say, hey, look at self.sharedObjects screens for the right screen, and there we go. I have access to everything. Let's see. I have to mention this too. If you're using PyQt, which I highly recommend, if you put this after any variable, actually, doesn't matter what this type is. If you have a something that it doesn't, or that Python or PyCharm can't autocomplete on, if it doesn't know what the type actually is, like it doesn't know what this is, well, on assignment. If you put this here, it overrides the autocomplete type for this particular element, which means that when you type a dot after here, you'll get all of the autocompletes for the Qt widgets QLCD number class. And that's all you have to do. And it works through the whole file. Really makes doing fast work a lot easier. Something else you'll probably notice immediately, I write very, very long-winded variables, very long-winded method names, everything. Like, I don't shorten stuff. You should be able to read it the way that it works. So on ARM status update received callback, it's very definitive about what it's doing. You know that what you're getting is the data in a callback on what the ARM status is. And then I'm saying, hey, the shoulder comm state has an update that's ready, and that update is that it's going to be processing the raw comms data into a human readable string of the data's shoulder comm status. Like, if you've been programming for a bit, this should be a bit more readable, albeit long-winded. And considering how much code I had to write, I felt it was a okay-ish trade-off for spending a ton of time commenting. I'm sure that somebody will let me know whether or not that paid off or not, but that's how I did it. Let's see, I'm not really sure what else I should talk about. Maybe a little bit about the video coordination, because that one is complicated. Essentially what you have is a two-stacked system of the video coordinator and the video receivers. So the video coordinator instantiates instances of the receivers, and the receivers do nothing other than look at ROS topics, read in data for a particular camera, tell the camera to change resolutions, do auto quality adjustment. It does all the lower level stuff, and then tells the coordinator when it has a video update ready that should be shown on the GUI. And the coordinator handles all of the high-level logic for switching which video is shown in which GUI element, for handling, enabling, disabling displays, for handling the little orange box that hangs around it when you do so. And there's a lot of logic going on here just to make that work. And then the receivers themselves have a fair bit of, a little bit of code too. I'd say that it's not, the code itself isn't hard in itself. It's just conceptually there's a little bit to get to figure out there. Hopefully you'll never have to touch this. The only reason you'd ever have to is if there was a new camera added that wasn't there before. And then the map system, I didn't write this one. I've got a decentish handle on it. It doesn't quite work the way I was hoping it would. Again, I didn't write it, and it's hard to communicate exactly what you want. And I can't fault the fact that it does work, and it was one of the big reasons why we did so well at competition. So can't be that upset. But one of the big things that the way that it's written right now won't allow for is for it to be faster. You won't actually get live updates, especially when you're doing things like panning and zooming. So if anybody's going to work on anything, I'd highly recommend trying to work on making this map system a little bit better. Just to talk a little bit about what I think it should do, is what I'd imagine is that you'd use the map stitcher to create a really, really, really large version of a map. So let's say you have an area, you determine a zoom level that you care about, and you say, okay, I want every tile in a half-mile radius from this area. And it's going to stitch them all together, and then you're going to show a viewport of that stitched together larger image. And that means that without even zooming off the bat, you could just start panning around, you could rotate the map around, you could do whatever you want to. And then when you zoom in, you're doing essentially digital zoom using the viewport, and going down to whatever limit you want and back out to the maximum. Maybe even do something intelligent, like once you zoom into a certain level, you'll switch the actual composited Google Maps image that you stitched together to a whole different resolution, or to a whole different zoom level, sorry. It gets complicated. Google has done it, but Google also has a ton of developers behind it, so might be a bit of work, but that would be one of the nicest changes, I think, because while the GUI was usable in terms of the map, it was not smooth. But yeah, so there's that. There are the control systems. Actually, this is definitely worth mentioning. These two files here, drive and camera control center and effectors and arm control center, are the ones that interface with the controllers. And there's a lot of useful stuff in here, and things that you can play around with, like dead zones and scalars for how quickly holding a stick in a particular position is going to send commands to move the arm or move the mining system or whatever it is. I can tell you right now that they're mapped to controllers with specific names. So the afterglow is the clear controller with the blue glow. If you want to see what devices are on the system, you can uncomment this, and at startup it'll print out all the names. And then, for example, over here, the drive and camera control center one is actually a Microsoft Xbox One S pad right now. There is a process for setting up these stick mappings that's kind of a pain, but has to be done. If the team does not buy a Xbox One S pad in the future, it'll have to be remapped to whatever the data coming back from that controller is. So what I'll say is there's this line here that you can uncomment, and what it'll do is it'll print out this code or these codes, and then the state. So it'd be like, the button south would return a 0 or 1, or the absolute reading for the x-axis would return a value from -32,768 to 32,768, or whatever it is. So basically all this is doing is it's a thread that constantly runs polls for events from the controller, and it says, okay, I got an event with a code and a state to go along with the code, and it uses this mapping to apply that state to the states library here, to the states dictionary, so that when you're accessing this states variable from the actual class, you say, hey, what is the state of the left x-axis, the left bumper, whatever it happens to be, and all this little thread here is doing is updating that state in the background while this class is accessing it. And then this class then says, oh, hey, I'm going to publish camera commands. What's the current state of the Y button and the left bumper and the right bumper and all that information, and then processes it and sends it as necessary, and you're all good to go. But yeah, so if you need a new controller, you're going to have to change that name based on the device name printed back here, and then do a remap of all the codes and the states for that particular controller, and then you should be fine from then on. I highly recommend, if you do go with another controller that isn't exactly this, do not use anything but an Xbox controller. It's way more pain, it's not as nice, and these controllers just feel really good. They have a really fine control, so just stick with an Xbox controller of some kind. Okay, I honestly think that might be about all I can give in this now hour-long video. I should give you a pretty good overview of how the software stack works, what I was thinking when I wrote it. There's a lot of code here. There's like 10,000 lines or more, or something like that, in all these files. There's a couple here, a couple ROS packages that aren't being used, but were things that we're getting ready for integration. For example, with like ARM's move, or ROS's Move It package for the ARM. I highly recommend you just kind of play around with it and see what I was doing. There's also things like the Z wrapper for working with the Z camera that I never got integrated. So yeah, there's plenty to play around with. At its core, the rover should continue working the way it was before. You can make updates to it, make updates to the ground station, but ultimately I'd recommend kind of going over the software package a little bit closer and figure out what everything does, because you really are going to need a pretty good understanding of the whole stack, the rover stack and the ground station stack and ROS and PyQt and everything, in order to really understand how it all ties together, how it all works. But it's all here. Hopefully I made it, names of variables and such shouldn't be too confusing. There are two nodes here that aren't in Python. There's Rover ARM, which is the C++ for handling and controlling the ARM when it's plugged in, and the Rover camera node. Those are both C++. Yeah, Rover camera is even super short. Let's see, I'm going to take a look at my notes here. Oh, one thing I will mention is that the IPs and usernames and passwords for everything right now, just in case I don't write it down somewhere. The Rover desktop has an IP of 192.168.1.15. Username is Rover, password is Rover. The Jetson TX2 is 192.168.1.10. Username is NVIDIA, password is NVIDIA. Let's see. The Ubiquiti radios I have in another video, but they are 192.168.1.20. That is the ground station radio. The Rover radio is 192.168.1.25. Usernames are UBNT for UBNT. I'm actually not sure what that stands for, it doesn't matter. And then it is Rover for life, ROVER, numeral 4, LYFE caret. And I will put these in a file just so that it's easy to get to, because those are kind of important. Another thing you're definitely going to need is a little bit of networking knowledge in order to make this all work. I highly recommend that at least while you're in a place that has Wi-Fi, you get a router that can run the alternate firmware called DD-WRT or OpenWRT or Tomato or any open source router firmware that will let you take an existing router and make it a client to a Wi-Fi network. So basically what that means is when I was working on the ground station and the rover and I wanted them to have internet, normally it would be kind of a pain to get all of them connected to Wi-Fi independently and deal with that, and then also having a separate network for doing like rover comms between the ground station and rover. So what I did is I put my own personal Wi-Fi router in the rover ground station box, and then installed DDWRT and told the router to connect to OSU access as a client. And what that meant is that I had a local network on the 192.168.1.x net, but that it was getting internet from OSU access, and I didn't have to think about anything more than that. As long as I was at OSU, the ground station would get internet, and then over the radio link, the rover would also get internet. Also, fair note, you don't have to use the radio when you're working on the rover. I didn't tons. You just plug in an Ethernet cable and you'll be good to go. Just keep in mind that it's going to be somewhat faster and somewhat lower latency than if you were to do it with the radio, so do testing. Let's see. I'm also going to post images of the controller layout, so how all of the controllers are mapped for all the controls as they are currently. I've also provided files in the GitHub repo that include the GIMP project files that I use to make those, so if you change it in the future, it should be pretty quick to change. And then the TX2 is mounted to an Avidea J120, I believe, carrier board, and it's what lets us have the Jetson in that nice little super tiny stack. We're not using the massive development board or anything like that. So long as nothing happens to the Jetson, everything is fine. If for whatever reason the software gets corrupted, you need to reinstall, whatever happens, just keep in mind you have to do some custom kernel additions to the Jetson in order to make it see the carrier board and all of its features properly. There is a guide somewhere on it. I haven't used it in like 6 months, so I don't really remember all that well. But you cannot just reinstall the Jetson TX2 with the stock firmware, flashed firmware, and just have it see the carrier board and work with no problems. You will definitely need to do some custom work. If I remember correctly, it was basically as simple as downloading the normal and Linux for Tegra package used to flash it in the first place, and then you copy some files into a location and you edit a config in one other spot, and then it was good. But just keep that in mind. I would avoid doing that if at all possible, or avoid reinstalling if at all possible. But I figured to mention it while I'm here. Let's see, that's all those items. I think that's actually it. That is pretty much the Rover software stack overall. There's also, oh, this is important here, a little quick start guide. Yeah, here we go. Let me drop this down. So here under the software tab, there's also a quick start document. So this was something I wrote that tells you, again, like here's how to launch the ground station or the rover or whatever it is. It talks a little bit about project structure, UI elements, how to work with PyQ's threaded classes. It's short, sweet, simple, but gets you started a little bit too. Yeah, modifying the software is not for the faint of heart. But do note that it is there. Otherwise, in the future, I can be contacted at caperrin@caperrin.com, and I can try and answer some information, but and just kind of have fun with it. I mean, most of what needs to be there for now is there. I think it's just going to be a matter of maintaining this and then adding little features as people get comfortable with it. So I'm just think I'm going to call it there. Have fun.